Exercise 4. An elastic spring R of negligible mass of stiffness K equal 50 Newton per meter. K equal 50 Newton per meter. Hangs vertically and carries at its lower end a small solid S of mass M equal 250 gram. From gram to kilogram, divide by 1000, so it's equal to 0.25 kilogram. This is the spring without mass, and this is the spring with a mass M of object S. This is the free length L0, and this is the final length L, and this is the elongation X. Part 1. Calculate at equilibrium the extension of the spring. That means the elongation X. Deduce its elastic potential energy. So, the forces, the external forces acting on S are weight and tension T. So, at equilibrium, part 1, at equilibrium, apply Newton's first law, sum of force external equal to 0. We have tension plus weight equal to 0. Projection along y-axis vertically upward. It's vertically upward. So tension is plus T and weight minus W equal to 0. So tension equal mg. By Hooke's law, we have T equal Kx. So we obtain Kx equal mg. Then X equal mg over K. Mass, it's equal to 0.25 kilogram times 10 over 50. It's equal to 0.05 meter. So this is the extension of the spring. The elastic potential energy EPE, it's equal to half Kx square. Then it's equal to half times 50 times x square 0.05 square equal, we obtain 0.0625 joules. Part 2. Let O be the position of the center of inertia of S at equilibrium. Then this O. This point is O. The reference level for the potential energy of the gravity is the horizontal plane passing through O. Then the horizontal line passing through O is the reference. We pull S from its position of equilibrium in O along the descending vertical by a distance B equal 5 centimeter. So S become here by a distance B from the reference or its equilibrium position. B, it's equal to 5 centimeter, then it's equal to 0.05 meter, since from centi to meter times 10 to the power minus 2. Calculate then the potential energy of the system Part 2, potential energy, it's equal to gravitational potential energy plus EPE. GPE equal mgh, but in this case the height is b, and when the object is below the reference, so GPE equal minus mgb, since it's below the reference, plus EPE equal half k. The elongation in this case it's equal to x plus b square. So we obtain minus 0.25 times 10 times 0.05 plus half times 50 times 0.1 square. It's equal to 0.125 joule. So this is the potential energy. Exercise 6. A solid S of negligible mass of stiffness K equal 40 Newton per meter. K equal 40 Newton per meter. S is subject to move on a horizontal ray x prime x at equilibrium. S is NO. At equilibrium, S is NO. So this is S. We move S at a point A. The spring is then compressed by a distance x equal 10 centimeter. X equal 10 centimeter. From centimeter to meter times 10 to the power minus 2. So it's equal to 0.1 meter. At the date t0 equals 0, we release S without speed. So V0 equal to 0 meter per second. At the date t1, the solid S passes through O with a speed V0, and the spring resumes its empty length. So at O, x equal 0, then not compression. So in this case, the spring is not elongated, not compressed. The reference level of the potential energy of gravity is the horizontal plane passing through the axis of R. So this is the reference. Part 1, indicate the form of the energy stored in the system Earth as R on the date t0. When the velocity is equal to 0, so kinetic energy equal to 0. And when the object is on the reference, so the gravitational potential energy equal to 0, then the energy stored is elastic potential energy. Elastic potential energy. Since S is at rest at t equals 0, so kinetic energy equal to 0 joule. Part 2, calculate the mechanical energy of the system at t0 equals 0. Mechanical energy equal kinetic energy at t0 plus EPE at t equals 0, and GPE at t equals 0 equal to 0 since the object is on the reference. Kinetic energy equal to 0 since the object is at rest, plus half kx square. We obtain half times 40 times x is equal to 0.1 power 2. We obtain mechanical energy equals 0.2 joule. Deduce the value V0 of the speed V0 at T1, x equals 0, so EPE equal to 0. And in this exercise, friction equal to 0, then mechanical energy is conserved. So ME at point A equal ME at point O. ME at point A, it's equal to 0.2 joule, and ME at point O, it's equal to kinetic energy plus EPE plus GPE. EPE equals 0 and GPE equals 0, so have VO square equals 0.2 have times and of mass 0.25 times V0 square equals 0.2. In this exercise the mass is missed, so by given mass it's equal to 0.25 kilogram. We obtain V0 equal 1.265 meter per second. Part 3. Find the speed of S when it's halfway between AO. Halfway, x1, the new x, it's equal to x over 2. Then it's equal to 5 centimeter, equals 0.05 meter. So we have ME is conserved since the friction equal to 0. So ME at T equals 0 equal ME1 in this position. The mechanical energy is equal to 0.2 equal half mv1 square plus half kx1 square. It's equal 0.12 equal half times mass times v1 square plus half times 40 times 0.05 square. 0.2 equal half times 0.25 v square plus half times 40 times 0.05 square. We obtain V1 square equal to 1.2 and then V1 equal 1.095 meter per second. Part 4 determines the magnitude of the spring tension when S has a speed V equals 0.8 meter per second. We have ME is conserved, so ME is constant equal to 0.2 joule. In another case, ME equal EPE plus kinetic energy. So EPE it's equal to mechanical energy minus kinetic energy. It's equal to 0.2 minus half mv square equal to 0.2 minus half times 0.25 times 0.8 square. We obtain EPE equals 0.12 joule. This EPE. And in another case, EPE equal half kx square. It's equal to 0.12 half and the k40 x square equals 0.12. We obtain x equals 0.077 meter. By Hooke's law, tension equal k times x, so T equal 40 times 0.077. We obtain tension equals 3.08 Newton. Exercise 7. A solid S of mass m equal to 100 gram. From gram to kilogram divide by 1000, so it's equal to 0.2 kilogram. And of small dimension is released without speed from the top O, so VO equal to 0 meter per second of an inclined plane. S moves along the line of greatest slope OA as shown in the opposite figure. R is a spring of stiffness K equal 40 Newton per meter. The horizontal plane passing through AX is taken as the reference level of the gravitational potential energy. Neglect friction, so friction equal to 0, and take G equal 10 meter per second square and OA it's equal 50 centimeter. From centi to meter divide by 100, so it's equal to 0.5 meter. Part 1. Calculate the mechanical energy of the system as spring earth. Friction equal to 0. So mechanical energy is conserved. Then ME of system, it's constant, equal to constant. Then ME system, it's equal to the mechanical energy at any position. So it's equal to ME at point O equal kinetic energy at point O plus GPE, gravitational potential energy at point O. The kinetic energy, it's equal to 0 since velocity is equal to 0 at point O. Then 0 plus mgHO. This is HO. So apply sine alpha. Sine alpha, it's equal opposite to hypotenuse. The opposite of alpha, it's HO, so it's equal sine alpha equal HO over hypotenuse, it's AO. Then HO equal AO sine alpha. Then mechanical energy of system equal mg AO sine alpha. We obtain 0.2 times 10 times 0.5 times sine 30. Then mechanical energy of system it's equal to 0.5 joule. Part 2. Find the speed of as it passes through point A. When friction equal to 0, then ME is conserved. Then mechanical energy at point O equal mechanical energy at point A. Therefore, 0.5 equal kinetic energy at point A plus gravitational potential energy at point A. While the object at point A is on the reference, so the gravitational potential energy is equal to 0 on the reference. So we obtain 0.5 equal half mVA square plus 0. 0.5 equal half times 0.2 VA square. We obtain VA equal 2.236 meter per second. Part 3. The solid S passes a point A and slides on a straight horizontal rod AX and compresses the spring R. Determine the maximum compression of the spring. At maximum compression, always kinetic energy equal to 0. And we have friction equal to 0, then mechanical energy at point A equal mechanical energy at maximum compression. So 0.5, it's equal to kinetic energy plus EPE. At kinetic energy at maximum is equal to 0. So 0.5 equal half kx square. We obtain x max. We obtain x max square equal to 2 times 0.5 over 40. K, it's 40. So x max it's equal to 0.158 meter. We need radical here to this quantity to obtain this value.